I'm now going to discuss some of the atomic mechanisms behind the interactions between matter and magnetism and the origins of ferromagnetism. A lot of this is very phenomenological, and this is part of an electromagnetism course, not a solid state theory course. To understand magnetism properly, you need a great deal of really quite sophisticated quantum mechanics and solid state theory, which we're not going to go here, but the basic ideas are correct. So for diamagnetism, I'm actually not going to discuss anything at all, because the key ideas can be found in Griffiths. He gives a nice phenomenological, though entirely incorrect, description of electrons orbiting an atom as if they're a current loop. He does acknowledge that it's not correct, I hasten to add, but it does describe the basic idea that when you have a current loop with an external field, the external magnetic field will induce a change in the current loop, which will give you some kind of induced moment. That's how diamagnetism works. Essentially, you can do it in a more sophisticated manner, but we're not going to. So let's start with paramagnetism, where we can derive quite a good model just from some simple ideas. So we're going to assume that each atom has a little dipole with a dipole moment m0, and of course the energy of that dipole moment in an external field um is going to be given by minus mu naught he dotted with m0, and here he is the external field. So this is some kind of applied external field. And we can, of course, then write that as minus mu naught he m0 cos theta, where we're only using magnitudes. Okay, so that's true for one dipole moment. Now we're thinking about a piece of matter which is made up of large numbers of atoms, so we have to turn to statistical mechanics. And so in general, we would find that the probability of a given moment having the energy is going to be proportional to an exponential of minus over kt. Now we're going to define a parameter, beta, which is dimensionless and is very convenient, so that's given by mu naught m0 he, that's the external field, divided by kt. And so now we could write the probability of having the energy is given by e to the minus beta cos theta. So cos theta is giving us the angle between the field and the moment. Now, if we were to integrate over all of these moments in a sample using the partition function, then in the usual way, I'm not going to go through this because it gets quite tedious, partition function fn, then what we can show is that the magnetization m of the entire sample, is given by the following. It's given by effectively the total number of atoms in the system multiplied by the statistical average of m0 cos theta, in other words, the likelihood of that happening, which can be shown to be n times m0 times a rather horrible function, which is coth beta, so that's the hyperbolic cotangent, minus 1 over beta. And you will see this function, coth beta minus 1 over beta, referred to as the Langevin function. That's of no particular importance, and we're not going to think about it in any other place. You should just know that it exists. You can show that for small values of beta very much less than 0, then you can approximate the Langevin function, which is coth of beta minus 1 over beta, by beta over 3. And if we use that, then we can show that the magnetization m is given by n m0 beta over 3. If we substitute in for beta, then we get the following. We get m times m0 squared times mu naught he divided by 3 kt. And that, of course, tells us that chi m is going to equal n m0 squared mu naught over 3 kt, which is just proportional to 1 over t, and this is the Curie law, or Curie's law, depending on how you want to use your possessives. So the key point here is just to understand that simply by starting from an assumption of a magnetic dipole moment, looking at how those dipole moments will be distributed given an external field and doing some statistical mechanics, we can derive Curie's law. This only works for large temperature values, it's only reliable for large temperature values, but it shows us why we get this kind of behaviour. Now, what about ferromagnetism? Well, ferromagnetism is complex, fascinating, and sometimes extremely horrible. And what we're going to do is we're going to look at what's called Weiss's law, or the Curie-Weiss law. Let's actually give Curie his due. The Curie-Weiss law, because this is just an extension of Curie's law. We are going to use what's called a mean field model. In other words, we're not going to consider the interactions between individual moments in the material. We're simply going to consider the field of all other moments on one particular moment. And so what we're wanting to do is to explain the behaviour of ferromagnetism. So what Weiss suggested was we introduce some kind of new field from the internal moments. So how would we do that? Well, what we do is the following. We write HE prime, if you like, is equal to HE plus gamma M. I'm not putting vector signs on there. They should all be aligned. And notice here that gamma is equivalent to 1 over something like chi m, just so that you've got that. Now, if we do that, then we're going to substitute for beta, and we say that beta prime is equal to mu naught m naught over 3kt into, sorry, not 3kt, just kt. We're going to get the 3 later. He plus gamma m, wrong m, gamma m, which we can then write as mu naught m naught he over kt, which of course is the original beta multiplied by 1 plus gamma m over he. Okay, so what that's doing is it's showing that introducing this kind of internal boosting field, it's called the Weiss molecular field, simply enhances beta. So it changes that. It enhances the field and therefore changes beta. Okay, so what's the effect of this? Well, what we find is that m, the magnetization, is now equal to n m0 into coth of beta prime minus 1 over beta prime. Please note that in particular here beta prime is very, very much less than 1, and so the temperature T is large, and we'll say what it's large with respect to in a moment. So now you expand this out and you use that approximation. You say that n is equal to n m0 squared mu naught over 3kt, there's the 3, into he plus gamma m. Okay, so we can rearrange that for m, and we can also define the following temperature. We define Tc is equal to gamma mu naught m naught squared n over 3k, and please remember n here is the number of moments in the system. And so when we do that, we can write the following. We can write that m is equal to n m0 squared mu naught he over 3k into t minus tc, which tells us that chi m in this case is equal to some constant t over t minus tc, and this is the famous Curie-Weiss law. I mentioned this as an observation in the previous video, that in a mean field model, the power of t minus tc is minus 1. If you do the calculation properly, or if you go and do an experiment, you'll find that that power changes to something more like minus 1.3 or minus 1.4. So again, the key point here is to show that by making some kind of assumption, in other words, that we can model ferromagnetism just by including the effect of the other moments in the system, then we can produce a formula that matches some experimental observations. And I noted in the previous video that the behavior of chi-m changes depending on whether you're above TC or below TC. And this approximation to TC is probably only describable as qualitative. It's not an accurate prediction. Okay, so that's just shown that you can make some kind of predictions using an atomistic model. If you want to understand ferromagnetism properly, then you really have to go drill down into the full quantum mechanics, and we're not going to do that. Let me just give a few observations on the atomistics of what's happening in a ferromagnetic material. So we start on the atomic level, and on the atomic level, we find that the individual magnetic moments align parallel to each other. This is due to the exchange interaction. It's quantum mechanical, and as I said in the previous video, it's actually down to the electrostatic interaction between electrons and the Pauli exclusion principle. This is a very short-ranged force, but it's very strong. And so what happens is that, let's just say it's a short-range strong interaction. That's probably a better word to use there. So what we do is we build up what are called domains. So these are small groups of atoms, and when we say small, we probably mean 10 to the 4, 10 to the 5, 10 to the 6. It could get larger depending on the system. Where in an individual domain, all of the atoms are going to be aligned, and so I'm going to use a single arrow to indicate the overall magnetic moment of the domain. Now, thinking about the magnetic interaction between domains is going to be very similar to thinking about a bar magnet. If you have two bar magnets, they really don't want to align parallel. If you try and do that, you'll have to push quite hard to get them close together. They tend to align in opposite directions. And so what you'll find is that in a ferromagnetic material, you'll have other domains which are either anti-parallel, or in some cases you'll end up with some kind of structure where the domains are all oriented like this. It will depend on the history of the material. This is a lower energy than having all of the domains aligned. And notice that now we've got a longer range interaction than the atomic level short range interactions. This is also going to be weaker. And so, of course, when you apply an external field, then these domains will be affected by that field. The individual, or the domains themselves will want to orient, and the atoms will want to orient alongside the external field. So we'll get various processes. So first of all, domain walls will move. Domain walls are simply the walls between domains. That seems obvious. Let me just give you a sketch. So if this is a domain here where I've got all of the atoms aligned like this, then I've got another domain over here with all of the atoms anti-aligned. Then at the very simplest level, a domain wall is what's going on here, where you've got, this is what we would call an abrupt domain wall, where you've got one atom on one side pointing up and the other atom on the other side pointing down. You also get various forms of domain walls. You get some kind of systems where the atoms will rotate as you move from domain to domain, and you might say that your domain is here and then your other domain is here, and this area is probably known as the domain wall. So you can see that actually if you were to move a domain wall, then you're actually flipping individual spins rather than trying to rotate the entire domain. So domain wall movement is relatively cheap compared to full domain movement. And in fact, people are playing with moving domain walls on the nanoscale as a form of magnetic memory. You do also get domains rotating if you have a strong external field. And therefore you end up with magnetization. This is why you end up with permanent magnets. The reason that you get some of the other behavior that you see in ferromagnetism, such as remnants and the need to apply a field, an inverse field, an opposing field, to bring the magnetization back down to 0 is because there are all sorts of complex structures going on. So the material microstructure will matter, and that will include things like the grain structure of the metal. It'll include defects and various other things. So once you start trying to understand the behavior of a large piece of iron in an external field, then you have to look at all sorts of different levels, both atomic and domain level, at the crystal level, the microcrystals, the crystal structure, the grain structure, and larger scale things. So that's a brief discussion of the atomic mechanisms that you see in magnetism. It's largely been qualitative, but it covers most of what you need to know in terms of a basic understanding.